Hi there. So we're going to talk about molarity, and that's a unit of concentration. So instead of just saying something is dilute or something is concentrated, we can actually quantify it, and molarity is one way to do that. The symbol for molarity is big M, and it's defined as, those three lines mean defined as, moles of solute, so that's what's dissolved, divided by liters of total solution. Liters, of course, being a unit of volume. Total solution, remember, is your solute plus your solvent. So that total volume is your number in the denominator. So here we have an example of two solutions to the left there. One of them is 0.2 molar, and then the other one is 0.5 molar. So because they're colored solutions, can you figure out visually which molarity belongs to which? Looks like the darker one is going to have the more concentrated molarity. So the 0.5 molarity is going to go with the darker one. That's more concentrated. And then the more dilute one, or the less concentrated one, will have the lower molarity. So in this example, we have a 0.75 molar copper 2 chloride, or CuCl2 solution. So this copper 2 chloride, that's our solute. And then you may always assume that we are working in aqueous solutions in this class. So that means our solvent is water all the time, even if we don't specify. So I want to show you that the way you write this, you're going to rewrite this as a fraction. So anytime you see big M, that means molar, you're going to rewrite it as whatever the number is, so 0.75. And then remember, big M means moles of solute. Specific solute here is CuCl2, divided by 1 liter of total solution. Okay, now you can leave off this word solution here, but look at what you just did. You just made a conversion factor out of this molarity. And that's going to be really useful when you use these in stoichiometry problems or other dimensional analysis problems, when you recognize that big M is just a conversion factor that relates moles to liters. Don't forget, you're always allowed to flip your fraction. So you could also say in every 1 liter of this solution, there are 0.75 moles of the CuCl2, right? You're always allowed to flip your fractions. Here we have our graphic organizer that we use for stoichiometry. You can see that you have moles of A in one color and then moles of B in another color, and that's showing that you would actually switch substances here using your mole ratio. But more generally, when you're just working within one substance, you can go from moles to number of particles using Avogadro's number. You can go from moles to mass using the periodic table and molar mass. You knew how to go from moles to volume if you had a gas at standard temperature and pressure, and there are 22.4 liters in every 1 mole. But now we can add something to this. You can also go from moles to volume of a solution if you know its molarity, using big M. Okay, and big M is the number of moles in every 1 liter. So this is a connection also to stoichiometry. And when you're using molarity in stoichiometry, it's called solution stoich. So we're going to do an example. The question is, what mass of KCl is dissolved in 4.0 liters of a 0.62 molar KCl solution? So pause the video so that you have enough time to copy it down. Okay, so first of all, our KCl is what is dissolved. So that's our solute, okay? And then remember what we said, we can say that water is always going to be our solvent. I'm not going to give you questions where it's not. The next thing that I said to do, anytime you see molarity, split that apart into a fraction, make that a fraction. So rewrite this as 0.62, big M means moles of the solute, the KCl, over 1 liter of total solution. Okay, and that 1 liter does not count as sig figs. It doesn't limit your sig figs. It's exactly 1 liter. So it could be like 1.1 million zeros after it. So in this particular problem, in any problem, you want to look at the other number that you're given, okay? And my tip is don't start with the molarity. There are ways to do it where you can successfully accomplish what you're being asked with starting there, but my hint is to not start with the molarity. Instead, use the molarity as one of your conversion factors. So that means we would start with our 4.0 liters, and that's of the solution, over 1. Okay, and keep in mind what we're looking for in the end. We're looking for mass of KCl. So units of mass are going to be grams. So we're looking for grams of KCl. Okay, so when we use our dimensional analysis, we want something where we can cancel out liters. Okay, and the good news is we have a molarity, which has liters in it. So we'll put liters on the bottom, and we can go, using our molarity, to moles of the KCl. And I'm going to fill in the numbers. 1 goes with liters, 0.62 goes with the moles. And now my liters cancel. And then we're going to go from moles of KCl, and you know how to do this. You can go to grams of KCl. And we're going to do that using the periodic table. Okay, so when you add up the molar mass of K and of Cl, you're going to get 74.55. And remember that molar mass in the periodic table always goes with grams, and that's in every 1 mole. Okay, now the moles cancel, and you're left with grams of KCl, which is exactly what we wanted. So on our calculators, we're just going to multiply 4 times 0.62 times 74.55. Okay, so take a minute and do that. Get your answer. Also figure out significant figures. Okay, so when I do that on my calculator, I get 184.884, but obviously I can't have that many significant figures. So let's look at sig figs. I have 2 sig figs in my volume, and I have 2 sig figs in my molarity. So now you have more than just one given. So you're going to go with the fewest number in both of your givens. So if one would have 2 and one would have 3, I'd still only go to 2. In this case, it makes it easy because they both have 2. This 4 is not going to round the 8 up. So I don't write 18, but I write 180 because that last 0 is not significant. So our final answer is 180 grams of KCl that would be dissolved in 4 liters of a 0.62 molar KCl solution. Okay, if instead of a 0.62 molar solution, I had a 1.62 molar solution, then you would expect a lot more of KCl to be dissolved. If I had, a 0.2 molar solution, then a lot less of the KCl would be dissolved. So in review, molarity is a quantitative measurement of concentration, and it's defined as moles of solute over liters of total solution. The other thing that you should know is that big M is the symbol, and always rewrite as a fraction whenever you see big M. So for example, if we have 3.5 molar HCl, you can convert that to 3.5 moles of our solute, which is HCl, in every 1 liter of the total solution, which would be the HCl dissolved in the water. And then this is what you're going to use in your calculations. Good luck.